My name is Jakob Mcbroome, and I am a fourth-year graduate student in bioinformatics and biomolecular engineering at UC Santa Cruz in the Corbett DTIG lab. I earned my undergraduate degree in ecology and evolutionary biology at UC Davis, and after a short period in industry, I returned to graduate school to develop my computational skills. My recent research has mostly been focused on tool development for SARS-CoV-2 epidemiology and contact tracing. One of the major challenges of the pandemic has been the sheer scale of the data. Phylogenetic analysis, or the reconstruction of ancestral genomes, much like a family tree, is critical for contact tracing and tracking the evolution of new lineages. Unfortunately, existing tools designed for small and sparse data sets largely failed to adapt to the dense and ever-expanding SARS-CoV-2 sequence data, leading to extremely high computational costs or outright failure to keep up with demand. In response to this need, my group develops new approaches for pandemic-scale parsimony phylogenetics. The key innovation allowing our software to scale is the mutation-annotated tree, an extremely efficient data structure leveraging evolutionary compression to store and distribute millions of genomes in less than a gigabyte of data. Using this powerful storage format and highly optimized tools, we now maintain the global phylogenetic trees used for the identification of new lineages and variants of concern. This short clip shows the growth of our global SARS-CoV-2 phylogeny from about 240,000 samples to more than 3.5 million samples from 2020 to today, more than a tenfold increase. And the depicted tree only encompasses data from completely public sources, less than half of all sequences available. As a part of this group, I have written software for the use and analysis of files containing mutation-annotated trees in multiple programming languages, leading to publications in scientific journals. Additionally, I have developed an approach to automated heuristic SARS-CoV-2 transmission cluster identification, efficient enough to be updated daily with all available data. A transmission cluster in this case is the set of local cases descended from an infected traveler who entered the region. To make this approach accessible to public health offices, I designed a website which provides a visual platform to explore daily identified transmission clusters and their putative origins. This website includes an interactive map displaying the number of clusters identified across the United States. By selecting one state, it can instead be colored by a scaled representation of the flow of SARS-CoV-2 from each other region to the selection, in this case, California. In the future, I plan to continue to work to bridge the gap between bioinformatics and epidemiology, leveraging pathogen genome sequence information to guide public health policy.